Hello, this is Dr. Marion Carroll, and I'm teaching general chemistry to pre-nursing students at Dillard University in New Orleans, Louisiana. And so we want to continue with part 2 in chapter 4, where we were discussing acids and bases. We didn't get to discuss our Bronsted acids and bases, but we'll talk about these in context of making a buffer. So what is a definition for a Bronsted acid? It's simply a proton that we represent with a hydrogen, a proton donor. Something that donates hydrogen. And of course, a base is a proton acceptor. This can be clearly seen when we do a titration of a acid with a base. And a titration is simply a gradual addition of, let me draw it over here, we have a beaker, alright, and we want to start with an acid. Okay, so our acid is in the beaker in solution, and it's at a specific concentration. And we add gradually, kind of using a pipette or a burette, with a little stopcock on it. We add gradually to this a solution of acid, a base. And of course, this base is at a specific concentration. And while we're doing this, we want to measure the pH change. So we put a pH meter, we hook it up as a gauge here, and this will give us a reading of how much the hydrogen ion concentration is changing. Okay, based on measuring pH. And so this is a titration. And we typically represent titrations graphically. So I want to draw my coordinates for my graph. We have the x-axis, right, and we have a y-axis. And on this axis, it's not very straight, but it will be adequate enough. We'll be looking at hydroxide ion concentration going up as we go along the coordinates of our x from 0 to some concentration of hydroxide or base. Okay. And then on our x-axis, we want to represent pH. Okay, and we can begin pH down here around 1. And then we know what our scale is. Where does our scale end? 14. Okay. So we want to begin our titration with an acid, as I described here, but the acid can't be something like, and I'll show you this so you recall, let's say HCl. Alright, you remember why we can't use this acid to titrate? This acid is a strong acid, and what is particularly characteristic of a strong acid is its ability to completely ionize. That means the ions that form hydrochloric acid in water will completely ionize to hydronium ion and chloride ion. Alright, there's very little, if any, reverse or of this reaction. This does not make a good buffer or a good acid for a buffer. What we need is a weak acid or a weak base. Something like acetic acid. Acetic acid is a weak base, and I'll show you why. As we add base to a very acidic solution of acetic acid, the pH is going to go up fairly rapidly. So we're going this direction with our base in the titration that I showed you earlier, and the pH goes up. It will keep going up until it reaches a point where the buffer region starts to form. And what is a buffer? I haven't defined it yet, but I can define it here. A buffer is a solution that maintains pH. Simple as that. How do you maintain pH? Well, this is an example of maintaining pH. At about a pH of 4.8, which is right about here, this would be considered the center or the midpoint of our buffer range. And why is it the midpoint? Well, it's at this point where the concentration of our weak acid, COH, and its conjugate, CH3COO minus, are equal. This is where the pK equals the pH. So the pH at this point is 4.8, approximately 4.8 according to my scale. This is the optimum buffer region, because if I were to add more acid to this side, to this solution, then the acid will be absorbed by this conjugate base. Which is what the acetate here is. And if I were to take away hydrogen ion, okay, by adding more hydroxide, this hydrogen ion can be absorbed by the base so that the pH will not change. And this is a weak acid. So this weak acid and its conjugate are both at equal concentrations at this point, and the pH resists changing as high as this point. I would say that's 5.8, and it will resist changing as low as this point, 3.8. So at 5.8, the pH, if we continue to add base, is going to go up fairly rapidly. And if we were to add acid, this pH would stay steady until it reaches a pH of 3.8, where it's going to drop precipitously very quickly. So a buffer region is a solution that maintains the pH, and it maintains it plus or minus 1 pH unit of the pK. Okay, pK is K is a dissociation constant, and if we take a negative log of the pK, we'll get if we take the negative log of K, that's pK. Just like the negative log of the hydrogen ion concentration is pH. Alright, we can continue to titrate this, and it will just continue to go up as long as we have a strong base to titrate it with until it reaches 14. But our buffer region is maintained around 4.8 and nowhere else. This is a monoprotic acid. There's only one proton that can be lost or accepted, and so this is what's referred to as a monoprotic acid. Alright, well, that's quite a bit that I've given you here. There is still more. Hopefully you were in class and took those notes. So I will continue in this series. I believe with chapter 6. We'll skip chapter 5, and we'll cover functional groups and saturated and unsaturated hydrocarbons. We'll talk again.